Assalamu alaikum. Welcome to the sixth lecture of natural language processing. So today we will wrap up our discussion on edit distance and then start with language modeling. So we had started talking about edit distance last time. Edit distance is basically a measure for quantifying, is a measure for string similarity. And to compute the edit distance efficiently, we had to solve an optimization problem, and we used the generic algorithmic approach called dynamic programming. And dynamic programming in the context of edit distance is basically filling in a 2D space of values, 2D cells of values, a matrix of values, and in a structured way. And we also talked about that once, while you're computing the edit distance, you're also aligning the two strings. So alignment is a consequence of finding the edit distance. So through the alignment, we are able to find out which string, which character in string, the first string is deleted and which character in the second string is inserted, and which characters are in both strings are substituted. So these are the three operations that are allowed in the edit distance. So today I will wrap this up and then we'll move on to language modeling and we'll be starting with the probabilistic approach to language modeling. So before I get started, are there any questions?
Sir, midterm ke liye, is there any tentative date?
Could you repeat the question?
Is there a tentative date for the midterm?
Um, I have not decided it yet. I think we can decide it in this lecture. If you have any suggestions, you can make those suggestions and we'll decide it probably in the next lecture. So I think it should be in the 7th week, and most likely it will be out of class timings. So we'll have to decide a time which is appropriate for everyone. It could even be a weekend. So we'll have to decide. So do you have any suggestions? So do we have a spring break this semester?
I don't think there's one.
ठीक है. ठीक है. So I'll let you know some tentative dates in the next lecture, inshallah, on Thursday.
Thank you, sir.
All right. So are there any other questions? So this is the minimum edit distance algorithm. Just a second. So basically, if we have two strings, x and y, x is of length m and y is length n, we want to compute the minimum edit distance between them. We define a matrix D of size m plus 1 and n plus 1. So from 0 to m and from 0 to n. So we initialize all values of this matrix to 0. And then we also initialize di0 to I and d0j to j. So this is the first one is of course deletion of a character from x. The second is insertion of a character from into y. And then we have a recursion where we fill in the value of a cell Dij based on the minimum of three possibilities. The first possibility is based on deletion of xi. So basically di minus 1 j is basically, whatever the value you have with di minus 1 comma j, you add 1 in it. So this is a deletion. The other option is di comma j minus 1 plus 1. And the third option is the substitution option. And this only applies when the two characters at I and j are different. If they are the same, then this is 0. So if they are different, then of course we add 1 or 2. We will probably add 2 if we are using the Levenshtein distance. So this is the recursion that will fill out the entire 2D matrix. And then along the way, so in this recursion, we are selecting a minimum from three options. So we also indicate a pointer to the cell from which this particular cell was filled, or from which this value was filled. So remember, we either go from I minus 1 or j minus 1, or both I minus 1 and j minus 1 to this cell ij. So we maintain a pointer to each of those decisions. So once we have reached the end, which is dm comma n, which would give us the edit distance, we can do a backtrace, and that backtrace would tell us the alignment of the two strings. So if you are going, for example, left, so there is an insertion of that character in the y string. And if you are going down, then there's a deletion of the that character in the X string. And if you're going diagonally, there is a substitution from that value to that value. So in this way, you can get the entire alignment. And then if, of course, if there is no change in the substitution, then of course the character would be the same, but still will go diagonally. So this is the algorithm for the edit distance as well as the backtrace. And this is the matrix that you get, and also the backtrace, the lines that trace the alignment of the two strings. And this is the alignment shown separately. So if a character is deleted from X, so below that character, you have an asterisk. If a character is inserted in Y, there is a character in Y and there is an asterisk corresponding to that character in X. And of course, if there is a substitution, the same character is changed. And if there's no substitution, the same character is obviously the same. So what is the complexity of this algorithm? So what do we need to do? We need to fill the entire matrix. So the dimension of the matrix, as I mentioned before, is m plus 1, which is vertical. Of course, in the visualization that we saw, the string x was on the vertical axis and the string y was on the horizontal axis. So m plus 1 vertical and n plus 1 horizontal. So if you want to write it in terms of big O, it's basically m into n. So you have to fill every cell. In the worst case, of course. Similarly, space, you need to fill the entire matrix. Again, you have to complexity is m into m. And for backtrace, you simply need to keep pointers, and the space and time for that is m plus n. So the worst backtrace would be you go down completely and then go left, or you go left and then go down. The best would be the diagonal. So that is O, big O, m plus n. So of course, as you can see, it's fairly efficient, linear in both the sizes of the string x and the string y. Any questions so far? Okay, so far we had talked about the Levenstein distance and the standard edit distance, in which we were assigning cost of 1 or unit cost to insertion and deletion, and twice the unit cost to substitution. And this particular case is called a Levenstein distance. But this algorithm can be easily modified for any other combination of cost, as long as those costs are positive, meaning that 0 or higher. So you can use the same dynamic programming approach to find the edit distance, which would then be the minimum cost for transforming string X into string Y, and you have given some specific values for those costs. So you can have a different cost for example, deletion. You can have for insertion, and you have a cost for substitution. And these costs could be, as I said, non-unit costs. They could be different. So now the question arises, why would we like to have different costs? Uh, so, and the answer to this is, for different applications, uh, we might have different, you can say, cost or uh, difficulties, you can say, associated with each operation. And to reflect that particular application, you can give them different cost. And for example, in biology and bioinformatics, you have different sequences and strings, and you would like to match. So you might want to give different costs to different matches and different operation, deletion, insertion, and substitution. So this is dictated by the application. So let's look at the simple application of string. So, so this variation of the weighted edit distance is called a weighted edit distance. And as I said, you are assigning some weights or different weights to deletion, insertion, and substitution. So let's say if you want to do spelling correction, and for spelling correction, you might want to give different weights. And this basically matrix that you see on this slide is showing you the cost for substituting a character on the vertical axis, which is incorrect, or you can say the character on the horizontal axis, which is correct, with a character on the vertical axis, which is incorrect. So this is actually substitution cost. So for example, if you look at it, for example, if you want to move, if let me see. Let me see, I've written some of these values in the notes. Let me go there. So if the correct value was A and you incorrectly mentioned it as E, so the cost number that is given is 388. So A was correct, but you had incorrectly written E there. And if you reverse it, then it is 342. If the correct was E and you had given it a value of A. So what about M to N? So correct value was N, you had used M, so there's a cost of 180. So what about A and S? So the correct value was S and you had used A. So the cost is 35. So do you see any pattern here? So there are actually two things that are captured here. The first thing is that if uh, two characters are likely to be misspelled or used instead of the other, then we assign a higher cost to that. So for example, E and A. And in this case, both E and A are vowels. So we will assign a higher cost because this is a error that is common, or it might occur in, for example, many people because of the pronunciation in English. So E and A might be pronounced similarly, and they will use E instead of A or A instead of E. So we have assigned a higher cost to that. On the other hand, if you look at A and P, for example, A is a vowel and that was incorrect and the actual value was P, so the cost there is 0. So that is very unlikely. So that is very unlikely. So we have assigned it a very low cost, in which in this particular case 0. The other thing that is captured in this cost matrix is the proximity of proximity of these characters on the standard keyboard. So for example, E and A are relatively close together. So you might get an error of typing. Similarly, M and N is very close. So someone might mistype it. So that is also likely. So when an error is more likely, you tend to assign it a higher cost to ensure that it doesn't occur. While if you look at A and P, of course, A and P is also unlikely because of A being a vowel, P being a non-vowel, and very unlikely that someone who wanted to write P would write A based on pronunciation or any other issue. But it's also unlikely because A and P are very far away on the keyboard. So, you can assign cost, any arbitrary cost values to your operations and then apply your added distance to find the minimum cost for transforming one string to the other. And as I said, the cost would be defined by you, and they will typically would depend on the application. So the weighted added distance form, the algorithm is very similar. The only difference that you see is wherever previously we had added a 1 for a deletion, we will now add the cost of the deletion. And wherever we have added 1 for the insertion, we will add the cost for insertion. And wherever we added the cost of substitution, we will now add the actual cost of substitution. And the algorithm terminates in the same way. At the end of the day, the last cell, the top rightmost cell, would contain the minimum added distance between these two strings. And of course, this is a weighted form of the added distance. So that brings us to the end of this chapter, this section. And this slide is just for your general information, dynamic programming and its history. So are there any questions on added distance? So added distance is an optimization problem, a search problem. It is solved using fairly efficiently using dynamic programming. You get an alignment as well as part of the uh, added distance computation, and added distance computation can be easily be modified for different weights of those or cost for those three operations: insertion, deletion, and substitution. So last time we also talked about the Hamming distance. Hamming distance is for two strings that are of the same length, and it only looks at substitutions. So there are no insertion and deletions. right? And we also then talked about longest common subsequence, or LCS. This is actually a similarity. I think last time I did not make this clear. This is not dissimilarity. So edit distance is dissimilarity, and Hamming distance is also dissimilarity. This LCS is similarity. So LCS is basically uh, the length of matches in the two strings divided by, so basically the length of the common sequence, you can say, in the two strings divided by max of divided by, sorry, min of the length of string X and length of string Y. So of course, this is the normalized form of the longest common subsequence. We are normalizing it with the length, the shorter length in the two strings, so that it has a maximum value of 1 and a minimum value of 0. So once you have normalized it, if you subtract it from 1, then you get the distance. So in the standard form, it is a similarity. If you want to get a distance, you have to subtract it from 1. And of course, to find that numerator, which is the length of the common sequence between the two strings, you will have to solve the edit distance problem, or if in general, the alignment problem. So we have to align the two strings. Once you have aligned the two strings, then you can find the length of the two, the common length in the two sequences. So just to give an example, hypothetical example, let's say you have A, B, C, uh, and let's say J, K, L, and then you have another string A and KL, A and KL. So the matching, of course, is A with A, and then there's a gap in the first string, and then KL matches. So the longest common sequence here, of course, would be 3. So there might be gaps in between. And these gaps, how do you get those gaps? Through the alignment problem. So length of the common sequence in this case is basically 3. So of course, this is a simple problem. You can look at it and get the length of the common sequence. All right. So I think with that, we will conclude this section and this chapter as well, and then move on to now language modeling. So we had been mentioning language modeling quite a bit since we started this course. So now we are actually going to study what language modeling is. So language modeling is a fundamental concept as well as tool available to us in NLP. And the whole idea of language modeling is we would like to be able to model how language is written. So language, as we know, let's say in English, is a sequence of characters, and more appropriately, sequence of words that make sense or that have meaning. So we would like to capture correct sequence of words or grammatically and semantically correct language. So for example, I live in Lahore, for example. So for those of for people who understand English, they know this to be correct English, both in terms of spelling, both in terms of syntax, also in terms of grammar and semantics. All of this is correct. But if I just flip this or write it in a different way, live I, NI, this is spelling error, and then let's say Lahore. So this sequence of words is not correct in the English language. So we would like to have a computational way of determining which one is correct and which one is incorrect. And as you can imagine, for such types of tasks, we rely upon probability theory. So, so in general, what do we want? So we want to find the probability of a sequence of words. So W1, W2, W3, and W4. Let's say a sequence of 4 words. So we want to find this probability. And if I find this probability for the first sentence, and if I find this probability for the second sequence of words, the probability for the second sequence of words will be much smaller. So in other words, probability of I live in Lahore would be much greater than, or should be greater than, probability of uh, live NI Lahore. So language modeling essentially is assigning probabilities to sequences of words in running text. So that is language modeling. And once we are able to assign probabilities, we can do a lot of things. So in this particular example, you can easily find out that the first sequence of words is correct and the second sequence of words is incorrect in the English language because its probability is higher than the second. So, and then of course, you can do various things. You can do language generation, you can do uh, other things as we'll see later on. For example, you can be, you would be able to determine the grammatical usage of words. So for example, verb, noun, adjectives, pronouns, and so on. So what is the correct usage of these parts of speech in the English language, for example? So all of this can be done through probabilities and through language modeling. And also through language modeling, you can do simple things as classification as well. So let's say you have uh, two corpus. So let's say, so first corpus is of positive uh, so positive, for example, sentiment. So you have various tweets that are of positive sentiments. So let's say you have various documents D1, D2, D3 that are all positive. And then you also have negative sentiment document. And let's say here again, you have D1, some other D1, not the same D1, of course, D2, D3, and so on. So if you learn the language of the positive documents and you learn the language of the negative documents, then you have what is called a conditional language model. So you will have something like probability of, let's say I have a new sentence W1, W2, W3, given the positive, and I will also be able to compute W1, W2, W3, given negative. And if, for example, the probability for the positive was higher than that of the negative, you can do a classification. You can say that this document will contain W1, W2, W3 is positive with a greater likelihood as compared to it being negative. Okay. So this is the general idea of language modeling. And as I said, it has various applications. We'll be seeing many of these applications throughout this course. So now let's go back to our original formulation. So what we wanted was find the probability of any sentence. Let's say a sentence with 4 words, 3, W4. So using our probability theory product rule, you can write this as part of so W4, let's say, given the context, which is in this case W1, W2, W3, then probability of W1, W2, W3. So this is simple application of the product rule. But while we are applying this product rule, we are keeping in mind the sequential nature of the words. So we had defined the first term as probability of W4 given the context that was preceding it. And then, of course, multiplied by the context, which is W1, W2, W3. In the more general form, you can actually do anything. So, for example, W1, W2, W3, W4. You could also have written probability of W1 given W2, W3, W4, probability of W2, W3, W4. So this is also possible in probability theory, but we will prefer the first formulation because in that case, we are talking about the word W4 after having seen the previous sequence of words. That is more common in NLP. So for example, if you are doing speech detection, so you are processing speech in sequence. So you have seen a particular or your particular uh, uh, output. Of course, in speech detection, let's say you have transcribed it, for example. So particular textual element, which is W4. So if you are now currently looking at W4, you have previously already looked at W1, W2, W3. That would give you better clues of what W4 should be. Okay. So we prefer the first breakdown, although the second is also possible. And sometimes it's used, but rarely in NLP. Okay. So, and then you can do this recursively. If you look at the first, again, I wrote probability of W4, given W1, W2, W3. And the second term here, I can break it down again. W3 given W2, W1, W2. And similarly, I can break the third one again, W2 given W1, and then finally W1. So I can break it down into these many terms, right? Again, simple product rule applied recursively to the probability. So is this clear? So this is essentially it. So in other words, in language modeling, we would like to estimate. So right now it was just writing it in terms of probability formulas, but the whole thing in language modeling is how do you estimate these probabilities? So we would like to estimate the probability of W1, W2, W3, and W4. So we like to estimate this. To estimate this, we can also estimate W1 and W2 given W1, and similarly the others, W3, and so on. So estimating the right-hand part is going to be relatively easier rather than directly estimating the left-hand part. And we will discuss this why it's going to be easier. Okay, sorry. So now how to estimate these probabilities? And that, of course, is the model. Once you have estimated all probabilities for a particular language, that essentially is called the language model, because then you can use it to find the probability of any sentence or any sequence of words. So, of course, all of you are familiar with, or I think most of you should be familiar with maximum likelihood estimation, which in a very simple sense is simply a ratio of counts. Okay? So, so, and of course, to estimate, you need to have a corpus. And what do I mean by a corpus? Corpus is basically standard, should say, basically collection of text in the language. So sometimes we also call this a running text. So it could be a book, it could be multiple books, it could be multiple pages from the web, it could be anything, as long as you have those sequence of characters and sequence of words. So that would be our corpus. And from that corpus, let's say if you want to estimate probability of W1, let's say, and let's say, let me give it an example, probability of I. And if I use the maximum likelihood estimate approach, so this probability estimate, I put a asterisk, a apostrophe there, I is simply the count of I in the corpus divided by the total number of tokens in the corpus N. So this is the maximum likelihood estimate for this word or probability I. Okay? Now, let's say we have a longer sequence of words. So let's say, so he, what should I write? Any longer sequence of words. Okay, anyway, anything that comes to mind. Stayed up all night to study. Okay? So this longer sequence of words, he stayed up all night to study. You want to find the probability of this. So what would you have to do? According to MLE, we have to find the count of the whole sequence in the corpus divided by n, you can say, but of course now you have to slightly different from n because now we are using a longer sequence of words. But let me just write n there. Slight difference. If the corpus is very large, n or n minus 3 or 4 would not make a big difference. So now the question is, so how many times would you be seeing this complete phrase in your corpus, even if, let's say, assuming your corpus is very large. So he stayed up all night to study. This whole sequence of words is very unlikely to occur, maybe even once, and certainly not more than one, and usually it might be even 0. So what do you get for such longer sequences? Whenever you try to find the estimate, you will get a value of 0. So the whole challenge in probabilistic language modeling, especially in NLP, is to find better ways of estimating these probabilities. Because language is highly ambiguous, and we are unlikely to find the same sequence of words, even if you take a very large corpus multiple times. And if you don't see a sequence of words multiple times in the corpus, then the estimate would be very poor or very noisy. And that is something that we would like to avoid. So any questions so far? Any questions? So I have already uploaded these slides on LMS. And of course, these are the book slides with slight modifications here and there. If you have directly downloaded them from the website, that should be fine as well. Okay, so okay. So the rest of the discussion on language modeling would be, which would continue for today and maybe the next lecture as well, would be on how to estimate these probabilities in a more effective way, uh, and to overcome some of these issues that arise. Even if you have a very large corpus, you are unlikely to see the same sequence of words multiple times. So the first thing that we do is, again, going back to our theory. So we said that probability of W1, W2, W3, this is only 4 words, W4 can be broken down into probability of W4 given W1, W2, W3, and probability of W3 given W1, W2, and then probability of W2 given W1, and then of course probability of W1. So this is simple application of product rule. But again, if you look at the second term here, so this term here, let's say if you want to estimate this term, so if you want to estimate this term, what you need to do, you need to find the count of W1, W2, W3, W4, and divide by the count of uh, the context, which is W1, W2, and W3. So again, the same problem arises here, meaning that you will need to find the whole sequence of those words in your corpus. And it's, if the length of the sequence is large, you are unlikely to find many or even one uh, count, even if your corpus is very large. So what do we do is we make some assumptions, again from probability theory, and that is called the Markovian assumption. And we say that the probability of a particular word only depends on the preceding word only, let's say, or whatever your context is. So in this case, let's say if we say only on the preceding word, then the whole sequence is reduced. W1 and W2 is removed in the context, and only W3 remains. So in other words, is approximated by this expression here. So the context is now limited to only the preceding word, not all words preceding it. So if you do this, then the above expression would then become W4 given W3, probability of W3 given W2, and then probability of W2 given or W1, and then finally W1. So we have now simplified the right-hand side to only two terms. One in the context, one is the actual term, probability. So in other words, we are only retaining the preceding context, the preceding word in the sequence as the context. So this particular assumption and this particular formulation in language modeling called a bigram model, meaning that you're considering only two words at a time. So in this particular case, for example, probability of the estimate for this W4 given W3 would be what? Simply the count of W3, W4 divided by the count of W3. So you only need to find counts of two words in sequence in the corpus, which is much more likely to to be in multi to be in kind of, you can say, more robust rather than being noisy. So this formulation where you consider only two words, or in other words, when a particular word probability only depends on the preceding word, is called a bigram model in language modeling. And in general, you can have trigram, and you can also have a trigram model when context is two words. And in general, n-gram model. So context is n minus 1 words. Okay? And the special case is Unigram model. Unigram model, no context. So let's say if you wanted to estimate probability of W1, W2, W3, and W4, using the Unigram model, you simply have W4 multiplied by W3 multiplied by W2 multiplied by W1. So this is the Unigram model. And then, of course, if you wanted to find any of these estimates, W1 is simply count of W1 divided by N. Okay? So these counts are likely to be more robust, meaning that you are less likely to get noisy estimates for probabilities. Any questions? So in this slide, you see that if you build a unigram model, meaning that you have a model in which you have estimated the probability of every word from a large corpus, and then they have used that model to generate uh, no context basically means that you're not considering any preceding word. So basically, so if you wanted to view W4 given W1, W2, W3, we have approximated this by simply saying it's a W4. There is no context, no given condition associated with W4. So wherever W4 occurs in the corpus, we will count it and use it to estimate the probability of W4 irrespective of what appears before it. All right. So we are talking about, let's say you have a language model, you have built a language model. Or you can say developed a Unigram. So if you have developed a Unigram language model, then you have probabilities for or estimates for probabilities for all words, single words. Probability of I, let's say, probability of the, probability of and, probability of, let's say, Asim, probability of Lahore, and so on. So you have estimated all of these probabilities. And once you have these estimate available with you, you say that we have a language model available. And in this particular case, it's a Unigram language model. And using this Unigram language model, you can estimate the probability of any sentence. For example, if you want to estimate the sentence of I, Lahore, and Asim, you simply take probability of I multiplied with probability of Asim multiplied with probability of Lahore, right? So you can find the probability of this sequence. So this is the Unigram language model. Of course, as you can see, the Unigram language model completely ignores the context and it might have issues. So let's say if you use this Unigram model to generate language. So generate language, how? So you have a distribution over all the words. So you have probabilities for each word in the corpus, in the vocabulary. And those probabilities, based on their distribution, you sample a word. So let's say you sample a word and you found that you get the word the. Then you generate a random number again, and according to that distribution, you sample again, and maybe you get the word I. And maybe you sample again and you get the word the again. And maybe you sample again, maybe you get once a Lahore somewhere, and then you get the again, and so on. So the sequence of words that you get would be closely related to those words that occur frequently in corpora. And those sequences would not make sense in a language. Okay? But let's say you have developed a bigram language model. So in this case, you now have probabilities of two words. So for example, I am ka probability hai, probability of Lahore University की है, and probability of he is की है. So now if you use this distribution to sample bigrams, you might get two words that are more meaningful. He is, so this is one sequence. Maybe you might get another, let's say, whatever, and again, let's say, and let's say I am, and so on. So as you can see, if you increase the model length and use that model to generate, you will get more meaningful sequence of words because they will be capturing correct usage of words in the corpora. Any questions? So as you can see in this figure, these sentences you can say do not make much sense, but they do reflect words that occur very frequently in running text. Okay. So if you think over a Bigram model, so this model, of course, is conditioned on the previous word. So there is a context of one preceding words. So if you use such a model to generate text, you will get two words that are more meaningful. So parking lot, Lahore University, so on. So couplets, two words would make more sense. So in general, as I said, you can extend this to n-gram models. But for most applications, we typically go to trigram or maybe 4 grams. Because if you go to higher n grams, as we mentioned earlier, estimating those probabilities become a challenge, and you won't find meaningful estimates for those probabilities, even if your corpus is very large. So far we are only considered smaller dependencies. So longer dependencies are usually not captured in the standard probabilistic language model. We'll see more language models later on using neural networks. They are better able to capture longer dependencies. So we have already looked at estimating, the simplest way of estimating, which is the maximum likelihood estimate. Uh, so this is a very simple example, but I think just quickly go over it. So let's say you have 3 sentences. So the first is I am Sam. And we also have added a token S to indicate start of sentence, a token \S to indicate end of sentence. And we will consider those as part of the sequences as well, just to find out where a sentence is likely to start and where it is likely to end. And the second sequence is slam I am. And the third is I do not like green eggs and ham. So based on this very small corpus, just for example sake, you can use maximum likelihood estimate to find various probabilities. Where is it? So for example, if you want to find the probability of I given S, so you'll need to count number of times that S and I occurs in this corpus, it occurs twice. And then you'll divide it by the number of times that S occurs, which is the context, which is 3. So the probability of I given S, which is starting of sentence, is 2/3. And here, of course, this is bigram estimate. So you have 2 words at a time. So let's say we have a huge corpus for restaurants and their reviews and people's comments on those restaurants. So you will have various sentences. Some examples of those sentences in this corpus are given here. So from a language model that's built on this, and let's say we are building a bigram language model. So you will be counting the occurrences of 2 words in a sequence, and you can represent those counts in a 2D matrix. So the vertical axis represent the first word, and the horizontal axis represent the second word. And each such cell would give you the number of times that particular word occurs in the corpus. So given any corpus, you can fill this 2D matrix, which is the bigram count, raw bigram count. And from this, of course, you can also then compute the bigram probabilities. So these are the probabilities that are computed based on that. So simply, basically, taking the count and dividing it by the sum of all those counts. So let me go back here. So if you look at this, matrix, so the vertical axis, let's say you take any word, let's say eat, EAT. So this word, and then after that, let's say you have Chinese, eat Chinese. So the cell there would indicate the number of times that eat followed by eat and then Chinese occurs in the corpus. So if you sum up the entire row of eat, this would be the sum of all the times that eat occurs in the corpus, right? Similarly, actually, if you sum up all the times that eat occurs in a column, that's all should be the same if you have computed the full matrix. So let's say if you want to find the probability of or you want to find the probability eat followed by Chinese, or basically Chinese given eat, you take the count of eat Chinese and divide it by the count of eat. The count of eat is the sum of all the counts that you see in the row of eat. Okay? So that would give you the probability of Chinese given eat, which is given in this table here. All right. So once, let's say you have estimated bigram probabilities from a corpus, you can estimate the probability of any sentence using those estimated bigrams. So basically, if you have a sentence, I want English food. So what would you do? You find the probability of food given want. I want English food. So food given English, then English given want, and want given I, and I given starting sentence. If you multiply all of these bigram probability, you get the probability for this sentence. Right? So we are multiplying this. So food English, and of course, end of sentence also. Food English, English want I, and then I start of sentence. If you multiply all of these probabilities, you'll get so you'll get a value. Obviously, probabilities are less than 1. If you multiply multiple probabilities that are less than 1, the final probability will be even smaller, which is obviously makes sense, because if the probability of a given word is less than 1, then the probability of exact sequence of words is going to be even lesser. So language model, we have talked about language model, how to estimate language models in the simplest form, of course. And we have also talked about how to use language model to generate language. And now so language model also encodes various interesting informations. So, and so for example, in this slide, you have, so want English ki probability, if you look at the probability, so 0011. So, want Chinese is, so 0065. So which one is higher? Want English, want Chinese? So want Chinese is higher. So you can right away say that people tend to like Chinese food more than English food. So this is, you can say, some information or knowledge that you have extracted or gleaned from this bigram language model. So, want to, so basically, if you want to find the probability of this is 0.66. So this is, of course, a restaurant and eating data set. So this occurs quite frequently. So 0.66. So, and if you have an incorrect sequence, so to food, the sequence to food is kind of incorrect language, and you notice that you don't find any such instance in the corpus, and you have a probability of 0 for it. So, so language model also give you insights into the corpus that you're analyzing. So obviously, as we saw, if you multiply multiple probabilities, you will get a very small value. So one thing that you can do is you can take the log and then do the addition. Log of the probabilities and then find the log probability. So in that sense, the calculation might become slightly easier. So this is something that you can do. Take the log of the probabilities and do the addition to find the log of the probability of the sentence. And of course, log is a monotonic function, so you can still compare the probability. If a probability of something is higher than another thing, then the log of that will also be higher than the other log of the other thing. So it's a monotonic function that retains the notion of relationship. So there's a very interesting, you can say, language, Ngram language model toolkit, or I should say toolkit, the viewer, which is called the Google Ngram. So Google Ngram viewer. If you do a Google search for the Google Ngram viewer, you will get to an interface which lets you study Ngrams that are learned from tons of books, lots of books over hundreds of years. And you can do various filtering on it. Maybe you look for a particular sequence of word, let's say since 1910 to 1940, and maybe you still look for the same sequence of word in 2000s. So you can study language in this way through this Google Ngram viewer. It's very interesting. It has very nice graphs and it does other things as well. So you should spend some time looking at this and getting familiar with how language is used and what probabilities that you get over a period of time. For example, 1800s and early 1900s English language, for example, the Shakespearean English had very specific and different spellings. So those spellings would occur more frequently in the period 1800 and 1900, while if you look at the same spelling of words in recent times, those occurrences would be very few. So you can actually spend a lot of time browsing this viewer, very interesting information. You can, of course, filter with various other options as well, part of speeches, proper nouns, and so on. If you take a look at it, it's quite extensive. So I think I'll probably stop here. So in the next lecture, we will talk about evaluation, which is primarily using perplexity and which is related to probability. And then after that, we'll look at some better ways of estimating probabilities. So far we have only talked about the maximum likelihood estimate. So that is still a problem for most NLP applications. So we would like to have better estimates for NLP, and we'll discuss those in the next lecture. Also in the next lecture, as discussed earlier, we'll be having a quiz at the end of class. So any questions? That doesn't make a difference. As long as you take the base to some consistent value, let's say use base 2 or base 10 consistently, so that should be fine. So, but if you want to be more puristic, I think, and you want to relate that to, let's say, entropy, then you can take base 2. But it doesn't make a difference in, I think, almost all applications. Any other question? So any other question? So as I said, next class we will inshallah have a quiz, and I hope the second assignment would also be due. I think probably would be released probably next week, not this week, probably next week.